Okay, so in today's lecture video, we're going to be talking about hydration, right? Keep in mind, every time we talk about a new type of reaction, you should have another 3x5 card that includes the starting material and reagent, and then on the back, a product, and if there is an important mechanism. We are going to be learning a place where mechanisms are important in hydrations, and then what we're going to do is build in a couple of new note cards that are what I call kind of witch's brew reactions, which are, we're not really going to talk about the mechanism of them. We're going to more care about being able to recognize what product comes out. So, first of all, hydration. You probably guessed that what we're going to be adding to a double bond in this case is an equivalent of water. So, thinking back to that kind of AB system, let's pick out a nice, simple, super simple alkene here. And let's look at water, but we're going to think about water in a slightly different way, right? We're going to, first of all, add a couple of new conditions in this. We're going to put an H plus catalyst in there. This reaction, at least the one that we're learning right now, requires just a tiny, tiny bit of a catalyst to get things going. And keep in mind, a catalyst isn't consumed in a reaction and has to be kind of reproduced throughout the reaction so that you don't actually consume it. And so it turns out what we're going to add to this double bond, in this case, is going to look like this. There's our equivalent of water, right? A couple of things you'll notice is that if you took this, right, and kind of imagined that this was our A and that was our B, really what we've done is we've kind of added the equivalent of a water, right, across that double bond. There's my A and my B. You'll notice a couple of things about this that we should probably write down. First of all, this is our Markovnikov addition, which means that that H is going to go to the less substituted carbon, just like we normally would expect for a Markovnikov addition when we were talking about HX addition. Another interesting thing, and we'll just write this down too, is that it goes through a carbocation, right? And so that's pretty similar. That carbocation, right, is going to be open to all the rearrangements that we talked about in the previous video lecture, so that's not going away. And that's actually part of the reason why we need to talk about some witch's brew reactions. And what those do is it are kind of ways to avoid the plus charge moving around and rearranging our carbon skeleton. So that's the reason that we're going to have to know a couple of those witch's brew reactions nice and early here. Luckily, I chose a starting material where this is just really simple, so we don't have to worry about that thing. So let's talk a little bit about the mechanism here. It's probably not going to surprise you to recognize that eventually, somewhere, I'm going to show a double bond kind of swinging out. Well, it turns out that the reason that we needed that H plus catalyst is that before we swing that double bond out, we have to do a step which I call sweetening the pot, right? It turns out that H2O in and of itself isn't kind of built to do this reaction perfectly. That's why we need this catalyst. So it turns out what this catalyst is doing is much like you saw probably in general chemistry. It's undergoing a Bronsted-Lowry acid-based kind of reaction where water is attacking the proton and you're ultimately producing what I will write is this, which is called hydronium, right? H3O plus. Now hopefully you guys can see that. So that H3O plus is more than strong enough to actually react with that double bond. So we have to do the pot sweetening step first in the mechanism, and then we're allowed to do our normal arrows. And I think last time I used red. So this goes through and attacks the H goes to the less substituted carbon. And just to stay consistent here, let's put our H there, and our H plus, and then of course, we've got this H2O floating around as a byproduct. Just like in the HX addition, now everything switches, whereas this thing was the nucleophile attacking an electrophilic species. Now this becomes the electrophilic species, and water comes in and attacks the carbocation. The problem is that we're not quite to the product at that point. We've gotten to something that looks pretty close to the product that we're trying to get to. Except that there's an additional proton on there at this point, right? And so there's our product, that's where we're going to. This has an extra proton. It turns out this is a really, really common problem in organic. You get to something that has a charge, like an intermediate that has a charge. How do you relieve that charge and get to something neutrally charged? Well, it turns out that if you have a bunch of H2O around, or H2O and some H plus catalyst, there's a bunch of water floating around in the solution. So this is a case where the solvent is also kind of the reactant. And so we're going to actually need another water around to do pretty much the same thing that it did here with our catalyst, but instead now this thing is going to reach in and remove an H so that we can go ahead and get to our ultimate product right there, right? And so this is called a proton transfer with solvent, and it's a step that we're going to see a whole bunch of times. And so it turns out that all things being equal, this H2O plus H plus catalyst is a pretty useful reaction for most simple containing starting material, or simple starting materials. I should mention, though, that organic chemists sometimes try to confuse you in the way they write this. Sometimes they'll just straight up write H3O+. Or sometimes they'll draw H2O and then something you identify as an acid, right? Or it might say dilute HCl or something like that. And so that tends to really confuse students. It's not something that I can really just tell you all the different permutations of. That's what your homework's for, right? You should be able to look at your homework and start to kind of develop this idea of, okay, what's the general class of what I'm looking at here? Did Sean talk about anything where there was some sort of acidified water around? So that's something that really is good to ask about in office hours and say hey, I think this is doing this. Is it the same as what you talked about here? And that's really going to help you guys kind of not miss the forest for the trees in organic, which is unfortunately one of the complications of learning organic chemistry. So we could go through a whole bunch of examples of this, but you got more than enough on your homework, or if it's not this homework, the next homework assignment. So what we're going to show now is we're going to deal with this problem of the carbocation, right? What if I want to add an OH group, Markovnikov, to something that's got a little bit more of a complex skeleton that I don't want to rearrange? That's where something called witch's brew reactions, and by the way, that's my name, not the actual name, is going to come to play. Okay, so let's say that we wanted this starting material to turn into that product. There's a problem if we're just going to use acidified water here, because we saw before this, when this double bond swings out and we put a positive charge on that secondary carbocation, turns out that this is very likely to do a hydride shift. We don't want that to happen, right? And it's really common that you want to avoid rearrangements because they're really hard to control. So wouldn't it be nice if there was some way that we could do the equivalent of our hydration, but in kind of a tricky way? That's where this kind of crazy mix of chemicals comes in. It turns out that if you want to do a reaction like this, and you want that H to still be the OH to still be added Markovnikov, with the big thing is no rearrangement, it turns out that you have a bunch of different choices, but the one that we're going to go with is what's called oxymercuration reduction. And unfortunately, the way that these things are symbolized is super complicated because it really does look like a witch's brew. Turns out that what you do is use this kind of mercuric 2 salt, right? And this is an acetate, that OAC is acetate. And of course, you can abbreviate that all kinds of different ways, just like you saw in Gen Chem, we could abbreviate acetate ions in a bunch of different ways. And with H2O, you're going to be able to kind of get the process started in such a way that you don't have to worry about rearrangement. And you'll notice that this is the oxymercuration part. This is the reduction part, so we're going to need an organic reducing agent, and at this point you have no experience, so I'll just give it to you. This is called sodium borohydride. In THF generally. And I should mention, like, there's other stuff I could list out down here, but for us it doesn't really matter, right? What we're looking for in terms of oxymercuration reduction is we're looking for mercury, right? For us, mercury is going to do one thing really well. It's going to add something to Markovnikov. And again, we could go through the mechanism, but this is a perfect example of where a mechanism doesn't really help us that much because it's kind of specific to mercury chemistry. The fact that you need a reducing agent also has to do with the way that mercury intermediate is its chemical reactivity. But this isn't a class in mercuric compounds, thank God. And so, like, these two steps, right, that anytime you see an HG, that's something where I want you to kind of have this red flag that goes up. I'm adding something Markovnikov. It turns out in this case, we're adding an OH Markovnikov. And this second step is a necessary step to kind of get that product to pop out. So this is a great example of a witch's brew kind of thing, and just to confuse you, of course, sometimes they'll list off all kinds of other dribble drabble. You know, this reaction was carried out at, like, on a Tuesday with 2 atmospheres of pressure, and it was like an 83-degree reaction, but all that stuff doesn't really matter. What we're really keying in on is this presence of mercury, so I might as well write it down. This is a specific hydration called oxymercuration reduction. It will always add OH groups in high yield Markovnikov, right? Super helpful to get us through some synthesis questions eventually. Interestingly though, you might say, well, that's awesome. I know how to add an OH to a Markovnikov position. What about, is there anything where I could add an OH in an anti-Markovnikov fashion? And what you'll notice is, as we continue to talk throughout these terms, is there is always some way to do the exact opposite regiochemical step. By the way, regiochemistry has to do with where you actually add important organic functional groups. So regiochemically, oxymercuration reduction puts your OH on the more substituted. The one we're about to talk about here, you're going to notice that we put an OH on the less substituted, which interestingly we couldn't do with a normal hydration mechanism. So today you're going to have a total of 3 note cards to add to your stack. Okay, same starting material. Now we've got an OH added to the less substituted carbon. Again, this is going to be a mechanism that we're not going to worry too much about. We're just going to kind of memorize the witch's brew that's required. This type of hydration, which is high yield and no rearrangement, and now what's called anti-Markovnikov. I'll just put anti-Mark, is going to be what's called Hydroboration Oxidation. And the necessary starting materials usually look like this. Usually start off with BH3, and there's that solvent that we've seen a few different times of THF. And then there's usually a second step involving some sort of oxidation with peroxide, right? So you see BH3, right? Boron in any way, just like we saw mercury before, there should be a little red flag that kind of raises yourself to recognize that when boron is around, that there's some sort of anti-Markovnikov addition to something. And the second step here is an oxidation. Relative to last time, it was a reduction. We don't really care about that too much. This is just something that's really good to put on a note card. It turns out this proceeds with high yield is really, really useful. So I think that is probably enough to talk about today. So what you should have is this, at least 4 note cards at the end of this week. I would even make one for kind of the rearrangement possibilities for both hydride and also alkyl shifts. It really is the best thing to do, especially for reactions like this, where you have no concept, like you have no history with this, right? It's really hard to memorize this kind of stuff. So I used to just hang it on my like bathroom mirror on little note cards. And after I saw it a bunch of times, I learned to recognize, oh, this is what I need to do to my organic species. Okay, I will see you guys soon.